All right, buckle up, everyone, because today we're diving headfirst into quantum singularity energy extraction.
QSEE for short.
QSE, right.
Yeah.
And let me tell you, the material you folks sent in, this is some seriously mind-bending stuff.
It's a real deep dive, that's for sure.
It is. It is. But hey, that's what we're here for, right? To untangle these complex ideas.
Absolutely. And this one, it really pushes the boundaries of what we think we know about energy.
No kidding. So let's start with the basics, the foundation, zero-point energy.
Ah, yes, zero-point energy, where quantum mechanics throws us a real curveball.
Because, I mean, come on, the idea that empty space is actually buzzing with energy,
Yeah.
it's just wild.
It is. It defies our everyday experience.
Totally.
But quantum mechanics tells us that even in a perfect vacuum, at absolute zero, there are these fluctuations, these uncertainties in the energy fields.
And those fluctuations, that's where zero-point energy comes from, right?
Exactly. It's a consequence of the Heisenberg uncertainty principle. You can't know both the position and momentum of a particle with perfect accuracy.
So there's always this inherent fuzziness, this jitter at the quantum level.
There is. And that jitter, that's the zero-point energy.
And we're not talking about some tiny, insignificant amount of energy here, right? The theoretical calculations for this zero-point field, it's mind-boggling.
It is. The estimated energy density is enormous, enough to, well, let's just say it could do some serious damage.
Yeah, I've seen the numbers. Enough to boil all the Earth's oceans in a teacup or something crazy like that.
That's one way to put it, but here's the catch. It's uniformly distributed, spread out everywhere equally.
So we can't just stick a straw in and suck it out.
Not quite. Conventional methods of energy extraction just wouldn't work.
It's like trying to sail a boat on a perfectly calm sea, no wind to catch, right?
A perfect analogy.
So where do quantum singularities fit into all of this? How do they help us solve this energy extraction problem?
That's where things get really interesting. The quantum singularity framework, it proposes a whole new way of thinking about the zero-point energy.
Instead of this vast uniform field, we're talking about concentrated pockets of energy.
Yes, highly ordered energy, potentially locked away inside protons, or even within the structure of space-time itself.
Whoa, hold on. So we're talking like tiny, ultra-efficient batteries woven into the fabric of reality.
I like that, a very vivid image, and what's even more exciting is that this energy isn't static, it's dynamic, potentially accessible through quantum processes.
Okay, so how do we tap into it? How do we unlock this trapped energy? This is where the electromagnetic pulses come in,
You're
right?
at it. The idea is to use precisely tuned electromagnetic pulses, think of them as keys, to interact with this network of quantum singularities.
And these pulses, they can trigger the release of energy.
That's the hope. They could potentially induce these synchronized phase transitions across multiple singularities, liberating a cascade of energy.
So it's all about finding the right frequency, hitting that sweet spot to make those singularities sing, so to speak.
Exactly, like a finely tuned resonance, maximizing the energy output.
It reminds me of that classic physics demo where a singer shatters a glass by hitting the perfect note.
Perfect analogy. It's about matching the wavelength of the pulse to the inherent properties of the quantum singularity network.
Okay, that makes sense. But the sources we've been digging into, they mention different models for how these quantum singularities might be organized.
Yes, there are several competing theories.
Some suggest a lattice structure, others talk about spin networks, even fractals. It's getting pretty abstract here.
Welcome to the cutting edge of theoretical physics, where things get a little fuzzy.
Fuzzy is right. But these geometric models, they have real implications, right? It's not just about pretty pictures.
Absolutely. Just like the arrangement of atoms in a crystal determines its properties, the structure of this quantum singularity network, it influences how the whole system behaves.
So the organization, the geometry, it's key to understanding how we can tap into that energy.
Precisely. Think of it like this. A pile of bricks versus a meticulously designed skyscraper.
Okay, I'm with you.
Both made of the same material, but their structure dictates their function, their strength, everything.
So the arrangement of these quantum singularities, that's what we need to crack to unlock their true potential.
Exactly. And that's where these different models come in, each offering a unique perspective on how this network might be organized.
All right, so let's break them down a bit, starting with the lattice model. What's the picture there?
The lattice model, it's probably the most intuitive, visually speaking.
Easy to picture.
Exactly. Imagine a grid, a network of points, each point representing a quantum singularity.
Like a perfectly ordered cosmic checkerboard.
In a way, yes. And this geometric arrangement, It would dictate how energy flows through the network, how it responds to external stimuli like our electromagnetic pulses.
So the lattice acts as a sort of framework, a guide for the energy.
You could say that.
Okay, now what about spin networks? Those come from loop quantum gravity, right? One of the contenders for a theory of quantum gravity.
Yeah, that's right. And it gets pretty wild because in loop quantum gravity, spacetime itself is quantized. It's not this smooth, continuous fabric like Einstein envisioned.
So it's more like a network of interconnected nodes, and each node could be a quantum singularity.
Exactly. And these connections between nodes, they represent the fundamental relationships in spacetime.
So instead of a smooth sheet, we're talking about a web, a network of interconnected points.
More like a tapestry woven from these quantum threads.
Okay, I'm starting to get a headache, but in a good way. And fractals, where do those fit in? I usually think of fractals as those trippy, self-repeating patterns we see in nature, like snowflakes or coastlines.
And you're right, fractals are all about self-similarity, patterns that repeat across different scales.
Zoom in or out, and you see the same shapes, endlessly repeating.
Exactly. And some physicists believe that the universe itself might have a fractal structure at its most fundamental level.
So instead of a neat grid, we might be dealing with this incredibly complex, interwoven network of singularities.
It's a possibility, and it would make things a whole lot more complicated when it comes to understanding how to interact with this network.
No kidding. But hey, isn't that what makes this whole thing so exciting? We're exploring the very edge of what we know, pushing the boundaries of science and imagination.
Absolutely. It's a journey into the unknown, and who knows what we'll find along the way.
I can't wait to find out. But before we get too lost in the theoretical weeds, let's bring things back down to earth a bit.
Good idea. We need to stay grounded.
How do we actually go about proving any of this? What kind of experiments could we do to show that we're actually tapping into this quantum singularity energy?
That's the million-dollar question, and that's precisely what we'll be tackling in our next segment.
Stay tuned, folks. Things are about to get real.
Welcome back, everyone. Ready to delve deeper into the mysteries of QSEE.
I'm ready. Let's get down to the nitty-gritty. We've talked about the potential of quantum singularities, this incredible energy locked away.
But the big question is, how do we actually get to it?
Right? How do we unlock that energy? The sources mention two key mechanisms: proton tunneling and phase transitions.
Let's unpack those, starting with proton tunneling. This is where quantum mechanics gets really weird.
Oh, I'm all ears. The weirder the better.
All right, so imagine a particle, let's say a proton, stuck in a box.
Okay, I'm picturing it.
Now, classically, if the proton doesn't have enough energy to overcome the walls of the box, it's trapped.
Makes sense. It can't climb out if the walls are too high.
Exactly. But in the quantum world, things get a little fuzzy. The proton's wave function, it actually extends beyond the walls of the box.
So there's a chance it could just sort of appear outside the box.
That's the gist of it. It's like the proton can tunnel through the wall even if it doesn't have enough energy to go over it.
Quantum magic. But how does this relate to energy extraction?
Well, if a quantum singularity holds energy in a specific configuration, think of it like a compressed spring.
Act with potential energy.
Exactly. We might be able to use these electromagnetic pulses to increase the probability of a tunneling event, releasing that pent-up energy.
So the pulse doesn't provide the energy, it's more like a trigger.
That's a great way to put it. It nudges the system towards a state where tunneling is more likely.
Okay, I think I'm starting to grasp that. What about phase transitions? I'm familiar with the concept in everyday life, like ice melting into water.
But with quantum singularities, we're talking about phase transitions at a much more fundamental level.
So not changes in physical state, but changes in the internal structure of the singularity itself.
Precisely. Imagine going from a tightly ordered state within the singularity to a more disordered state.
Kind of like rearranging the furniture inside the singularity's house.
I like that analogy. And just like with ice melting, these transitions can release or absorb energy.
So by carefully manipulating the internal states of these singularities, we could potentially unlock that energy.
That's the idea, but how do we prove it? How do we actually test this in the real world?
That's a good question. We need some solid evidence.
Absolutely. The sources suggest a few experimental approaches, one of which is looking for what's called resonant enhancement.
Resonant enhancement sounds familiar.
Remember our analogy of the singer shattering a glass?
Right, finding the perfect note to create that resonance.
It's the same principle here. We need to tune our electromagnetic pulses to match the natural frequencies of the quantum singularity network.
Like finding the right key to unlock the door.
Exactly. By hitting that sweet spot, We can maximize the energy release and show that we're actually interacting with these singularities.
Sounds promising. But what are we targeting with these pulses?
There are a few options, from simple collections of hydrogen atoms to more exotic materials engineered for quantum coherence.
So we could start with something relatively simple, like zapping hydrogen with finely tuned pulses.
It's a good starting point, and as our understanding grows, we can move towards more complex targets.
Okay, so we've got our targets, we've got our pulses. Now, how do we actually measure the energy release? What should we be looking for?
First and foremost, a net energy gain. More energy coming out than we put in.
We need to rule out just converting one form of energy to another.
Exactly. We want a surplus, a clear sign that we're tapping into a new source.
And besides just measuring the energy, are there other telltale signs?
Absolutely. The sources also mention looking for specific spectral changes in the emitted radiation.
Like analyzing the fingerprint of the released energy.
A good way to put it, if we see a pattern that matches what we expect from quantum singularity energy transitions, that would be strong evidence.
So we've got the energy surplus and these spectral signatures, but what about the protons themselves? Can we observe any changes in their state?
You're on the right track. Techniques like nuclear magnetic resonance could be used to monitor the state of the protons before and after the pulse.
So if we see a shift in the NMR signal, that means the protons have changed their internal configuration, maybe due to those phase transitions or tunneling events.
That's the hope. It would provide direct evidence that we're manipulating these quantum singularities.
This is all very exciting, but let's shift gears for a moment and talk about the bigger picture. If QSEE works, what would a power plant based on this technology look like?
That's where things get really speculative. The sources don't go into much detail.
But let's speculate a bit. It's fun to imagine.
Right. So at the core of such a power plant, you'd need a source of quantum singularities, maybe a specially engineered material.
Some kind of exotic crystal, something that maximizes quantum coherence.
That's a good bet. And then you'd need a system to deliver those electromagnetic pulses, maybe lasers tuned to the perfect frequencies.
It's like we're conducting an orchestra of energy, coaxing it out of these quantum singularities.
A beautiful image. But then comes the challenge of capturing and converting that released energy into a usable form.
That's a big one. We might need entirely new technologies for that.
Exactly. It's uncharted territory, but that's what makes it so exciting.
It sounds like building a QSE power plant would be a monumental engineering challenge.
Oh, absolutely. But there are historical parallels. Think about the early days of nuclear power.
When they first split the atom, it took decades to figure out how to harness that energy safely and reliably.
QSEE might follow a similar path, a long road of research and development before we see practical applications.
This has been a fascinating exploration, but I feel like we're just scratching the surface.
We are, and in our final segment, we'll delve into the implications of a cold start to the universe and its connection to QSEE, plus the role of temperature and the future of experimental verification.
All right, welcome back to the deep dive. We're in the final stretch of our exploration of quantum singularity energy extraction.
And we're about to take things to a whole new level, cosmic level, that is.
I'm intrigued. Lay it on me.
We've talked about these quantum singularities, these potential powerhouses, but there's a fascinating connection to the very beginning of the universe.
The Big Bang.
Well, that's the prevailing model, the universe starting hot and dense.
Right, a fiery explosion of creation.
But the quantum singularity model, it suggests something different, a cold start.
A cold start, huh? That's a whole different picture.
It is, and it has big implications for QSE, especially when you think about coherence.
Okay, coherence, that delicate synchronization we need for efficient energy extraction.
Right. Now imagine a hot, chaotic early universe.
Everything's just a jumbled mess.
It's hard to see how that level of order, that coherence, could emerge from that.
So a cold start, a universe born in a state of extreme quantum coherence that changes the game.
Absolutely. It sets the stage for a highly ordered network of quantum singularities to form right from the get-go.
So in this cold start scenario, the universe is already primed for QSE.
Precisely.
Yeah.
It's like, imagine a perfectly still pond.
Okay, I'm picturing it.
The slightest ripple can spread across the entire surface without any disruption.
Smooth sailing for those quantum waves.
Exactly. A cold, coherent universe. It provides that ideal environment for a quantum singularity network to emerge and flourish.
It's mind-blowing to think that the potential for this revolutionary energy source could be tied to the very conditions at the universe's birth.
It is. It really connects the microcosm and the macrocosm.
But here's the thing. Our universe isn't cold anymore. It's warmed up quite a bit since the Big Bang.
That's true. The universe has expanded, cooled, and become much more complex.
Stars, planets, black holes, the whole shebang.
But here's the key. Even though the average temperature has increased, there might still be pockets where that primordial quantum coherence persists.
Like hidden gems of order in a chaotic universe.
Exactly. Perhaps at incredibly small scales or in highly isolated systems, those echoes of the cold start could still be out there.
So even amidst the warmth and chaos, there might be these remnants of that pristine quantum coherence.
It's a tantalizing possibility, and those pockets, those could be the key to unlocking QSEE.
This is where temperature becomes so crucial, right? Finding that sweet spot, coherent enough to manipulate, but not too cold to be unresponsive.
Absolutely. Too much heat and decoherence kicks in, destroying the synchronization.
Like a delicate dance routine falling apart.
But too little heat, and the singularities freeze up, their energy becomes locked away.
So we need to find that Goldilocks zone, just the right temperature.
Exactly. It's a delicate balancing act, but controlling temperature will be essential for any successful QSE experiment.
It's like recreating a tiny piece of the early universe in the lab.
It's a bold ambition, but who knows what we might achieve?
Well, this has been an incredible journey. From the bizarre world of quantum mechanics to the vastness of cosmology, all in pursuit of this potential energy source that could change everything.
It's a testament to the power of scientific curiosity, following the trail of questions wherever it leads.
And sometimes those trails lead to the most unexpected and mind-blowing destinations.
To our listeners, thank you for joining us on this deep dive.
Keep asking those questions, keep exploring, keep that sense of wonder alive.
This has been The Deep Dive.
Until next time, keep exploring the infinite depths of knowledge.